Today I will finish off graphical models, and I will cover Gaussian processes. Okay, so what did we cover last time? We talked about directed graphical models, and why we need them, the meaning of a directed graphical model in terms of factorization of the distribution over the variables, and how from the graph you can directly read off whether two variables are independent given some other set of variables. Then we talked about the use of graphical models to describe a sort of statistical model. Then I talked about inference in graphical models, the idea of singly connected graphs versus multiply connected graphs. And then the equations for factor graph propagation, which is just simply derived from the sum rule and the product rule and the structure of the graph. That's where it comes from. So then, after talking about factor graph propagation, I related this to things like hidden Markov models and Kalman filtering models and so on. And I think we ended roughly here. And then I went and talked about this ranking system called TrueScale, right? OK. So let me just show you very quickly if I'm online. I don't know if I'm online. Let me see if I'm online. No. I might need to connect to. So.
Yeah, so I forgot about.
Oh, is the wireless not on?
Yeah.
It's not very important. OK. And then
It's on? Or
I don't know.
right.
It's OK. It's not very important. Maybe later. What I wanted to show you is that if you go to, is it one of these?
Yeah, it's this one.
The second one?
The second
or?
one.
OK. Yep.
Look out. Yeah,
I have to, yes. I'm going to trip. OK. OK, that's good. So I just wanted to show people, in case you're interested, that this TrueScale model is something that we cover in our master's level class that we teach at Cambridge. You might find this the material here kind of useful. It has links to several good textbooks in machine learning, and some of the slides, which are, somewhat overlapping, but not completely overlapping with what I'm talking about here. In terms of this TrueScale ranking model, we actually have some coursework that you can download, and it has the data and some files in MATLAB. And this has all the results of all those tennis games so that you can actually play with it yourself. Maybe get together in groups if you want and try it out for yourself. And this also allows you to compare Gibbs sampling with expectation propagation as two different methods for trying to solve this problem. So if I click on this, this is what that coursework looks like. 107 players, 1,801 games for the 2011 season, and then some exercises. If you use MATLAB, it would be very easy to do. Okay. Any questions about that? Yeah. Other things that you might find useful here are there is actually a nice exercise on Gaussian processes, which I'm going to talk about in this lecture today. So if you want to learn more about Gaussian processes, I just encourage you to try doing this, again, in groups. And then there is a third exercise on latent Dirichlet allocation, which I'm not going to talk about, but it's an interesting model for modeling text. Okay. All right. So what I talked about was a summary of graphical models and then how to do inference in graphical models. But now let's talk very quickly about learning the parameters of a graphical model. So imagine you have a graphical model like this, and that represents some factorization of the joint distribution over all the variables in the graph. And if I look at any one of these factors in here, for example, this one here, it says is the probability of x2 given x1. So now imagine, for example, that x1 was a binary variable and x2 could take 3 values, just for example. So this object here, this conditional probability distribution, is a 2 by 3 table where the rows sum to 1. Okay? So the parameters of this model, I'm going to call the parameters here theta 2. The parameters theta 2 control the distribution of the variable x2 given its parent x1 in this graph. So the parameters associated with all the edges going into every variable. So what's the learning problem? The learning problem is, imagine you're given the structure of a graph. How do you learn these parameters from data? Okay? So the parameters of this model can be represented as 4 tables. Table theta 1 has k1 entries. K1 represents the number of values for variable 1. So that would be 2 entries. Theta 2 has k1 times k2 entries, etc. And these parameters are called conditional probability tables. You'll sometimes see the term CPTs thrown around. And essentially, the elements of these tables represent the probability that some variable takes on some value given the value of its parents. So then there's just some notation here. These tables in general can be m plus 1 dimensional if you have m edges going into some variable. But we can always collapse all of the settings of the parents into one super variable so that the tables are all 2-dimensional tables, where all the possible settings of the parents are on one side and all the possible settings of the child are on the other side. So now what we want is we want to learn from some data set of observations the parameters of this model. Now the observations are going to be n examples of these variables. Okay? Is everybody happy with that? Raise your hand if you want me to explain that some more. Okay. Good. So assume you have a data set of observations. Each observation is a vector of all of the variables. And we have n of those observations. and we want to learn the parameters theta from the data. So the procedure I'm going to describe to you is simply the maximum likelihood procedure. What the maximum likelihood procedure says is take the likelihood function and maximize it with respect to theta. So the likelihood function here is the probability of the data given theta. And I've just said there are n data points, so each data point contributes one term to this product, which gives you the likelihood. Now, each one of these terms, in turn, is represented using the conditional independent structure of the graph. So the distribution of all the variables here, x1, x2, x3, x4, factors in a particular way. And so we can plug that factorization in here. And then when we take the logarithm of the likelihood, what we get is that the log likelihood is, well, the log of a product turns into a sum. So the log likelihood is a sum over data points, and then a sum over variables. So here we have just 4 variables. We have n data points. Each data point is an observation of all 4 of our variables. Okay? So sum over variables. The log probability of the ith variable given the parents of the ith variable for the nth data point. Okay? And then as a function of these parameters. Okay, so just to give you an example, let's just consider the simplest possible graphical model. x1 goes to x2. Okay, and let's assume both of these are binary variables. And let's say x1 is smoking, and x2 is a binary variable for whether somebody is a smoker or not, and x2 is something like lung cancer. I was going to be a bit nicer. Emphysema. Okay, emphysema. So bad thing happening to your lungs, but not necessarily cancer. Okay, so now you have a data set. Okay, so x1, x2, we have a data set of observations where this person doesn't smoke and doesn't get emphysema, this person doesn't smoke and doesn't get emphysema, this person smokes and doesn't get it, smokes and gets it, doesn't smoke and gets it, smokes and doesn't get it, smokes and gets it. Okay, so this is our data set. What's n? 7. Okay, so n equals 7. That's the number of data points. And the number of variables, I haven't really denoted that with any symbols. The number of variables is 2. Okay, just to make sure people are not confused. So we have 7 data points on 2 variables. And it's a fully observed data set, right? So for every patient, we observe both of these variables. Okay, so I'll make a note of that. Right. So you take the log likelihood for this model, you optimize it. It turns out that it's very easy to optimize the log likelihood. And then you do a little bit of math to figure out how to optimize this function. And then what you end up with is an incredibly simple result. The maximum likelihood solution, you probably can't see this in the corner here because it's a bit small. The maximum likelihood solution simply counts the frequencies and renormalizes them. Okay? So in this particular case, we have a 2 by 2 table, and twice we observe 0, 0. Okay, so this is x1, x2. 1, 0, we observed 1 2 times. 1, 1, we observed 2 times. and 0, 1 we observed once. Okay? So these are the frequencies. And then to get the conditional probability of x2 given x1, right? From these frequencies, what we end up doing is just normalizing the rows of this matrix. So we get, 2/3, 1/3, 1/2, 1/2. Okay? And that's our maximum likelihood parameter for this table. What's our maximum likelihood parameter for this? For this part? For theta 1? Anybody guess?
3/7 for normal, 4/7 for yes.
Yep. Okay. So it's a very simple result. I won't rederive it for you, but basically it comes from doing maximum likelihood with just counts and discrete distributions. All right, so that's easy. That's for discrete distributions and discrete variables. We can obviously generalize this to continuous variables, and we simply have to do a little bit more math to compute the maximum of this likelihood function. It might not end up being as simple as this. Now, if we have hidden variables, so if some of these are not observed, let's say I have a data set that looks like this. Okay? So now I have 7 patients. 5 of the patients, I've observed everything for them. But 2 of the patients, I have some missing data for them. Now, this is a very, very important realistic situation. In many situations, when you collect data, some of the entries are missing. So what do you do when you have missing data? Here is a naive thing you could do. You could just say, I'm going to throw away this data and just calculate everything from the observed data. But actually, that doesn't give you the maximum likelihood solution. Okay, throwing away data is not a statistically efficient thing to do unless you have huge amounts of data. It's not a really sensible thing to do. But you can do better than throw away the data. You can do something that I described a little bit yesterday, which is you can run the EM algorithm. Okay, and so what does that mean? Well, in this case, the EM algorithm says our goal is to maximize the log likelihood given the observable data. Let's call the observable data y. And the log likelihood is the sum over the hidden variables. It's the log of the sum over the hidden variables of the joint distribution of the hidden and observed variables. So in this case, we would have to sum over 1, 2 settings of x1 and 1, 2 settings of x2 here. Okay? And that's our actual likelihood function. And now we can optimize that however we want. Just fit it into some sort of optimization routine. But it turns out that a nice numerical procedure for optimizing this is to run the EM algorithm, where in the E step what you do is you fill in the missing or hidden variables. So you don't actually fill them in by assigning it a particular value, but you fill them in by assigning some probabilities. Okay? So in this case, I'm not going to do the EM algorithm for you, but you would initialize the situation with some parameter settings, and you might fill in this variable with something like maybe 3/7. Depends. There's a correct way of filling in the probabilities here. And then you might fill in that variable with, well, what is it? It's like, given that x1 equals 0, the probability of x2 is 1/3. That would be 4/7 maybe. That's not quite the correct way of filling it in because actually we know that the second value here is 0. So we have to use all of that relevant information to fill in the right values here. So you fill in the variables in the E step, and then in the M step you re-estimate the parameters. So you get some new theta hat 1 and theta hat 2. And then you, again, fill in new values in the E step because now you have better parameter values. And then you re-estimate the parameters and you iterate. And that is guaranteed to give you a maximum of the likelihood. It might not be a global maximum, but at least it's a local maximum of the likelihood. Questions about that? Yes, OK.
In a continuous case, because now we are talking about some discrete probabilities
right.
here. In continuous case, we are thinking about some distributions, yes? So we expect some distribution, and then you maximize its likelihood, yeah?
Yeah.
And for example, we can use also MCMC to make it, because MCMC can be used for looking for the best result. Absolutely,
exactly. So in the so here the problem is simple because you only have a binary variable. So a distribution over a binary variable is represented by one number. In other situations, even in discrete situations where you have multiple settings of the variable, what you really need to compute is a probability distribution over all possible settings. In the continuous case, you need to compute a probability density over the continuous variable. And that can be very hard in general, except in simple situations like linear models with Gaussian noise, then you can do all of this analytically. But if you have a nonlinear model or non-Gaussian noise or some other complicated situation, then the E step itself might be very expensive to do. And so you might want to just do MCMC here. And actually, I mean, I would argue maximum likelihood is not a very sensible thing to do anyway. So you could just do MCMC over both the hidden variables and the parameters instead of trying to find a single value of the parameters. OK? Any other questions? All right. So just to come to that point from before, in a model like this, rather than doing maximum likelihood over the parameters, we could also just do Bayesian inference over the parameters. And that just is the usual thing. We treat our parameters as unknowns, and we put a prior on the parameters, and then we compute the posterior distribution over the parameters given the data. OK? And so here's a table for parameter learning. We have two situations, an easy situation and a hard situation. The easy situation is when we have fully observed data. So the initial situation I talked about, this was a 1 and this was a 0 or whatever it was, right? Fully observed data, no missing data. And then maximum likelihood is very hard, very easy. You just calculate frequencies. Bayesian learning is also very, very easy. You just update Dirichlet distributions here. In the situation with missing data, then maximum likelihood is a little bit harder. You have to do some sort of iterative algorithm like EM. And Bayesian learning is also a little bit harder because you have to infer both the parameters and the hidden variables. Okay, so you have to fill in both the parameters and the hidden variables. And you can do something like MCMC for that, or variational Bayes, which I talked about before, etc. Okay, so that was parameter learning. And now let me talk about structure learning. So, in all of these pictures, I assume there was some structure, but can we learn the structure from data directly? Okay? So let's try that. So here is the problem of structure learning. Given a data set of observations, can we learn the structure of a graphical model? And we want to be able to, infer anything from, nothing is connected with anything else to, there are lots and lots of connections. So the graph structure is simply the set of edges in your graph. How do we learn that from data? There are broadly two different methods for doing structure learning. There is an sort of approach based on constraints-based learning. So the idea is you use statistical tests for conditional and marginal independence, and then you build the graphical model from those statistical tests. And then there is score-based learning, which computes some global score for the structure. For example, BIC, which I described yesterday, is one score that you can use to learn the structure of a graph. Or the marginal likelihood is one score that you can use to learn the structure of a graph. And then you try to find the structure that maximizes the score. And again, this sort of basic idea here of Bayesian learning, if you apply it to structure learning, for complete data, that's when you don't have any missing or hidden variables. Then it turns out if you have complete data, discrete observations, and you assume something known as Dirichlet priors, then the score for a graph is very easy to compute. So the score for a particular graph, what do I mean by that? Well, I'm just defining that to be the log of the marginal likelihood, the log of the probability of the data given the graph structure. And the probability of the data given the graph structure is simply the integral over all possible parameters of the likelihood with respect to the prior. Okay? Yep.
About the Dirichlet priors,
Yeah.
what is the interpretation of them here? I mean, is it like we have a discrete number of choices and priors give us the probability of each of the discrete choices?
Yeah, it's I'll talk in tomorrow's lectures. I'll talk a little bit more about the Dirichlet distribution because I'm going to describe the Dirichlet process. Okay, so to understand the Dirichlet process, you have to understand the Dirichlet distribution. But here is the basic idea. Let me just explain the Dirichlet distribution very, very basically. So consider a situation where you have a variable x that can take on three values, 1, 2, and 3. Okay? So the probability of x given some parameters, well, it's a distribution over three variables. Three values, right? So then this probability distribution is parameterized by a vector. Let's call it P1, P2, P3, right? Where we know that the sum over I of the PI equals 1, and that all the PIs are greater than or equal to 0. Okay? So in fact, we could simply call the parameter here P, this vector P. All right? So now, this is the likelihood function. We want to put a prior on P. So what is that? It sounds weird. It's a prior on distributions. That sounds confusing. But it's not complicated at all. It's a prior. It's a distribution on vectors that happen to be non-negative and sum to 1. Okay? So what's a distribution on vectors that are non-negative and sum to 1. Well, a very nice family of these distributions is called the Dirichlet distribution. Okay, and the Dirichlet distribution, you could say P is drawn from a Dirichlet distribution with parameters alpha, and that means that the probability of P given alpha is proportional to the product over I of Pi to the alpha I minus 1. Okay, this is just the form of the Dirichlet distribution. There is some normalizing constant. Let's call it C, and then it's Pi to the power of alpha I minus 1. That's the expression for the Dirichlet distribution. What the alphas represent are, in a sense, pseudo counts of observations with each of these different values. We'll talk about the Dirichlet distribution a little more. The reason the Dirichlet distribution is used here is, remember I said the beta is conjugate to the Bernoulli distribution. Well, the Dirichlet is conjugate to the discrete distribution. So essentially, or discrete or multinomial distribution. So essentially what that means is if I have a Dirichlet prior and I observe some discrete observations like these, then my posterior distribution over the parameters will also be Dirichlet. And I can compute everything analytically. And in fact, that's exactly the result that we have here. If you assume Dirichlet priors, then I can compute the marginal likelihood, this normalizing constant analytically. The integral becomes very easy to do, even in high dimensions. And there is an expression for it in terms of gamma functions. And the gamma function is just a generalization of the factorial function. So this is sort of like something you can implement in one line of MATLAB or Python or whatever. OK? OK, we have some echo. All right, good. All right, so so the great news here is that I can start with a graph, and I can compute the score for the graph from my data set, and then I can evaluate adding or removing an edge to the graph, and then seeing whether the score goes up or down. And I just do greedy search on that, and that's just the algorithm that you could use for structure learning. And then if you have missing data, then it becomes a little more complicated. So here's the structural EM algorithm for incomplete data. I won't go into that in any detail. And actually, I could talk quite a lot about this. We've done a lot of work on using variational Bayesian learning to learn the structure of graphs. But I'm going to sort of roughly skip that stuff as well. So in fact, I'm going to skip all of this. OK. So when you have missing data, then you need to do something a little bit more complicated because computing the score is not analytical. But you can always approximate the score. So let's talk a little bit about causality, because it's a very important topic. So learning causal relationships is fundamental to how humans think about the world and also to understanding the results of scientific experiments and thoughts. And obviously, if you have two variables and all you observe is the settings of these two variables, you don't know whether x1 caused x2 or x2 caused x1. Those are these two scenarios. Or maybe there was a hidden common cause, right? Like maybe there is some genetic factor that both makes somebody more likely to want to smoke and also causes them to have emphysema. Okay? So broadly speaking, the difficulty in causal inference is that it's very hard to know the difference between A causes B, B causes A, or there's some hidden factor H which causes both A and B. So all we know in general is maybe that two variables seem to be statistically dependent on each other.
Excuse me?
Yes?
Could it be also possible for A and B to be completely independent?
They could be completely independent, but just coincidentally happen to look like they're related to each other. It's a little complicated, right? Because, you know, you could, okay, I'll give you an example which is slightly complicated here. So if you consider the world stock market, and you consider the average temperature of the ocean, both of these things seem to be going up. So if you just measured these things, it would seem that maybe there is a statistical dependency between them, and it just happens that they're both going up with time for, possibly unrelated reasons, right? So it's a little complicated, and lots of philosophers think a lot about causality. But how do you tell apart between these different kinds of structures? Well, the cleanest way to tell apart is to do an experiment. And that was sort of, part of the insight between Fisher and, early 20th century statistics and applying it to, experimental design, the idea of randomization and so on and so forth. So an experiment involves doing a manipulation. So if I manipulate one variable and then I observe the other one, then I can tell whether the relationship goes one way or the other, right? So if I could, it's not ethical, but if I could force people to smoke, right, then I could measure the increase in the probability of getting emphysema that's caused by smoking. But I would have to maybe also do the experiment where I cause emphysema in somebody's lungs somehow, and then measure whether they become smokers or not. Okay? So these are obviously not very nice experiments to do, but in theory, this is the cleanest way of figuring out the causal direction. And there's a lot of very, very exciting research in the last few years on trying to understand causality. And I highly recommend lectures by Phil David at a summer school that we organized on causality, if you want to know. So these are on video lectures. Okay. Let's talk a little bit about undirected graphical models. So imagine you have an undirected graphical model and you want to learn the structure of the undirected graph from data. Well, the problem here is that the probability of all the variables depends on an intractable normalizing constant. Okay? So there is this, in an undirected graph, there is a normalizing constant because the probability is obtained by multiplying a bunch of non-negative functions. And this normalizing constant, in general, involves summing over all the variables. So for some simple graphs that maybe look like chains or trees, the normalizing constant can be computed exactly. Whereas for more complicated graphs, much larger than this one, the normalizing constant is not possible to compute exactly. So maximum likelihood learning of parameters is generally intractable. Bayesian learning of structures is also intractable. And there's some research that, a bunch of people, including myself and my colleagues, have done on how to learn the structure of these undirected graphs. So if you're interested in that, I can give you more pointers to that. But it's a difficult problem. Okay? And then I just wanted to briefly talk about scaling of Bayesian methods, in particular graphical model-based methods. And the example of TrueScale is a very nice one, because here's just a snippet of TrueScale from the original TrueScale paper, where they basically scale this up to run on millions of people doing message passing. And Microsoft also does a bunch of other applications of very large-scale applications of graphical models to predicting the probability that somebody's going to click on a link. And a lot of other sort of probabilistic models. People are interested in getting them to scale to very large data sets. Okay? So I talked about the theme here that I talked about was graphical models. And in a sense, they're very intuitive and computationally useful representation for probabilistic models.